Previously on the Younger Dryas.
Anyways, the most recent oscillation, which brought the Earth out of the Ice Age and spawned the Holocene that we're in now, the question arises, and it's a question that has no final answer to it, is the Holocene truly a distinct epoch from the Pleistocene, or is it just another interglacial period within the Pleistocene? In some ways, though, the Holocene seems kind of unique. And that's a discussion we definitely want to return to when we start looking at the impetus for the rise of civilization and the conditions that were conducive to the rise of civilization as we now know it. Because ultimately, what we're trying to do with establishing this contextual framework of the Younger Dryas and the transitions that it represents is to understand the rise of human civilization and possibly the fall of human civilization. They're not just of academic interest. I believe firmly that the Younger Dryas has a great deal to teach us about our own time and what the future potentially holds. We are getting to what to me is just the most exciting developments. And in looking at this, in effect, what kind of seeps through some of these papers about the psychology of these men and women who are making these studies and realizing that, wait a second, this is telling a much more dramatic story than we had visualized a generation ago. Keep these episodes concise.
Well, that was a good discussion, just to get the context of the different camps, and to make sure that people understand the difference between gradualism, catastrophism, why it's important, what the difference is, and where we are right now. Gradualism still has a hold on our education system and on society today.
Yes, because only within the context of gradualism can you claim that there is now an anthropogenically driven climate crisis.
Right. Which is a problem. All right, we'll leave it right there.
We'll leave it right there, and we're going to pick this up in our next episode, so stick with us.
Welcome to Randall Carlson's definitive work on the Younger Dryas, your comprehensive overview of climate change.
Hello, I'm Randall Carlson, and I would like to welcome you to another episode of Squaring the Circle, where we are not afraid to challenge sacred cows, cut through the smog of propaganda, and collect the dots that are being deliberately ignored and suppressed by the status quo. So, before we go on, I would like to, somewhere out there is my friend and colleague, Mike Robertson. I'm going to wave around in the ethers and see if we can make you manifest. Ah, there you are.
Voila.
Just like that. All right, so we're picking up where we left off in the last episode in this dissertation and summation, condensation. No, it's not really a condensation because we're going to try to lay out in a lot of detail as much background as we can muster on the Younger Dryas, because there's a lot of controversies around this time period called the Younger Dryas that served as the last gasp, I guess you could say, of the Great Ice Age. And this occurred after it appeared that the Ice Age was well underway to dissipating, to going away, to disappearing. The world was warming. And then suddenly, a couple of thousand years of gradual warmth were undone in an eye blink, perhaps in less than a year. Wow. And the planet went back into this abyss of full glacial cold for about 1,200 to 1,300 years. And then it came out of it. The planet lurched out of that period of cold as fast as it went into it, if not even faster.
And there's the mystery that coming out of it, right?
Yes, coming out of it. So the brackets of time that we're talking about here I'm sure most of the listeners and the students that are following this know quite well now the timing of it, but it's going to be somewhat less than 12,900 years ago at the beginning of the Younger Dryas to about 11,600 years ago to the end of the Younger Dryas. And we've learned some things about the history of the thinking, the polar wildflower, the the realization that this flower had appeared and disappeared, and then appeared again, and then disappeared in Europe, Northern Europe. And this was one of the things that first clued researchers to the fact that the climate had been changing quite
Mm-hmm.
dramatically from
Mm-hmm.
cold to warm and back again.
Mm-hmm. Mm-hmm.
So we left off in the last episode with the work of Maurice Ewing and William L. Don, and let's see, we actually let's back up one slide that we looked
Okay.
at with Maurice Ewing.
So here we go with the Younger Dryas season 1, episode 6 with Randall Carlson.
All right, good. Thank you for reminding me because from time to time I have a lapse of memory and I go, "Who am I again?" So it's always good to have someone around who will remind me when.
That's why I'm here.
Okay, so let's look at. Uh, let's remind ourselves. Here we go. Here's Maurice, and let's remember this quote. This was from 1956, A Theory of the Ice Age, and these were in his conclusions on the theories of the origin of the Pleistocene glacial climate and of the glacial and interglacial stages proposed here are in complete harmony with the doctrine of uniformitarianism. No external influences or catastrophic events are required to initiate or maintain these conditions. So in 1956, we're just a little bit 6 years past the midpoint of the 20th century, and we can see that uniformitarianism, also we could think of it as gradualism, are well entrenched, and they are seen as the backdrop, the conceptual framework by which we think of global change, of planetary changes, and so on, right?
Mm-hmm.
However, within the next few years, we're beginning to see the uniformitarian edifice showing some signs of fracturing, the first signs that we see. Um, so let's kind of get into that because that's what we've been sort of looking at. That's been the trend of our thinking up to this point. We introduced radiocarbon dating. We introduced Willard Libby, who invented radiocarbon dating in the early 50s, and how by 1956, when this article uh, was published in the scientific press, in the journal Science,
Mm-hmm.
um, radiocarbon dating, there was not much of a database to which one could refer in working out some sort of a temporal chronology.
Mm.
However, then we discovered that 4 years later, when we introduced the work of Bruce Heason along with Maurice Ewing, we saw that there was this transition in the way the verbiage was expressed
Mm-hmm.
because in the 56 paper, we're talking about a fairly abrupt, you remember this, the fairly abrupt
Yes.
change?
Yes. Which at a later date changed. They dropped the term fairly, if I remember correctly.
That's right. They dropped it. And they're now saying, yes, it was an abrupt change. Let's see. Let's see what came here in the package. 2 vials, not one, but 2 vials. This is the Apollo oil. Yeah, purchase this. There we go. Purchase this online. You get the extra bonus is you get an image of me on the label. Now, of course, this was in my younger years. Okay, maybe not quite shipped in bubble wrap, so nothing happens to it. Look at this. There we go. I love this salve. I love the salve. Yeah, I love this salve. Julie, in fact, gave me a wonderful back massage yesterday using the Apollo salve. So I've went ahead and got myself a supply that's going to last for a while. Just in case of the zombie apocalypse, I'll have some saved back because I would not want to have to exist in a post-apocalyptic world without my CBD from the God salve. Okay, so, however, Maurice Ewing was he was a brilliant scientist, and his work was pivotal in bringing our understanding of Earth change to another level. And we find his name interesting. If you are people out there who are following my research into Atlantis, will have recognized his name because he took part and helped organize some of those first seafaring expeditions that traversed the mid-Atlantic ridge and took dredge samples and sonar soundings and began this discussion and opening up the first mapping of the mid-Atlantic ridge. So he was instrumental in that. Anyhow, let's move on. And we'll quote from this also 1956 paper to we get a sense of taking the timing of these things into an actual number of years. So this is from David B. Erickson, who was also part of that early group, and he was very much one of the founders, you could say, of marine geology and oceanography. This 56 paper, which also appeared in the journal Science, was entitled Late Pleistocene Climates and Deep Sea Sediments, because what they were realizing by mid-20th century was that climate changes up in the atmosphere actually transposed themselves. They translated themselves into sedimentary signatures in the bottoms of the oceans, the bottom layer of the ocean bottom. The ocean bottom preserved a record of changes in the atmosphere and environment outside the ocean. Does that make sense?
It does. It's amazing thought, like how that could actually occur.
It is an amazing thought. And we're not going to explore too much in depth that right now, but here's one example. If the planet cools and warms between a glacial and interglacial, the ocean, after a lag period, does the same thing. It cools and warms. Well, the lives that are living, the planktonic life, which is in the water column, and the benthonic life, which is dwelling on the ocean bottom, that changes with changing temperature. So just like the polar wildflower, just like Dryas octopedalis, changes with changing temperature, so do the creatures that live in the water column in the ocean. See? Anyways, so now we're starting to accumulate some radiocarbon dates here. And Erickson says the radiocarbon dates, the climatic curve deduced from the foraminifera and the paleotemperature measurements indicate that the midpoint of the major change from glacial to post-glacial conditions occurred about 11,000 years before the present. This major change appears to be broadly simultaneous throughout the North Atlantic and adjacent seas, and it probably occurred in a time interval on the order of 1,000 years. Let's pause there for a second. 11,000 years. Now let's bear in mind, in 1956, the paleoclimatologists and geologists and other scientists that look at Earth history have refined the radiocarbon data curve, and they've been able to actually correlate against an absolute time scale, like, for example, the rings in a tree rings, or the layers in an ice sheet. They discovered that there was a deviation of up to almost 2,000 years by the time you get back into that times of the glacial interglacial transition. So what this means is that when you're looking at an older paper, you have to make an adjustment. You have to make a calibration. There's now constantly being refined and updated, the calibration data by which you can go year by year and translate radiocarbon years into calendar years. You
Mm-hmm.
often see CAL, right? And that
Mm-hmm.
usually means calibrated, but think of it also kind of mnemonically as meaning calendar years,
Mm-hmm.
right? So here we're looking at 11,000 radiocarbon years, but that translates closer to being 13,000 years in calendar years, which brings it up very close to the bottom, the beginning of the Younger Dryas,
Mm-hmm.
which is now somewhat less than 12,900 years. Okay, so that's the first point. The second point is they're looking at this broad span of time and thinking, without necessarily going into the background on it. Now, I'll just mention that at the time this is published, they're thinking, "Ooh, 1,000 years. That's a lot quicker than we thought it happened." Right? Because it was a process that was considered to be 10,000 or 20,000 or 30,000 years, the whole process. Now, this major change, as they are talking about, which
Mm-hmm.
appears to be broadly simultaneous, another important point, is because the question is if you go to a particular region, a particular location, and you find evidence that there was major climatic changes, major
Mm-hmm.
environmental changes, well, what is it telling? It's telling you that yes, whatever it was that occurred, it occurred this local area or this region. Doesn't tell you though, oh, the whole hemisphere or the whole planet was undergoing a change. You can't extrapolate from one site and then include that this is a planetary a scale event. That's why
Mm-hmm.
you have to go to multiple sites, right? Now, what's showing up here is that the research is revealing that this change, which is a very significant change to go from glacial to interglacial world, happened over a period of about 1,000 years, and they're saying it happened roughly centered on about 11,000 years ago.
Mm-hmm.
Okay, so that was this 1956 paper. So you can begin to see here now that the framework has shrunk from being processed glacial to interglacial, taking 10,000 or 20,000 years to complete. No, it's happened much faster than that. It happened perhaps over a short a time span as a millennium.
Okay.
Okay, so what I'm going to do is come up here to this work by Carl Sauer, I think, that we mentioned at the end of the last episode. Uh, just for background on Carl, he was an American geographer and professor of geography at the University of California at Berkeley from 1923 to 1957. During which year he became professor emeritus. He was known, or is known, by those who know the history of geography, that he was the dean of American historical geographers, uh, and author of an interesting book I haven't read, but I'm somewhat familiar with the contents. His 1952 book, Agricultural Origins and Dispersals. He was very interested in the dispersal of the human race about the planet, which is a extremely valuable, important, and interesting question uh, that I personally would like to know more about because it's very intriguing. Because ultimately, one of the great mysteries, I think, when we start moving beyond some of the established paradigms, it raises new and interesting questions about the origins of the human species on Earth. Because I don't think we've got it figured out yet. Okay, I think there's more to this mystery of the human presence on planet Earth than conventional scholarship has recognized so far. Anyways, I'm going to go through and I'm going to read a little bit from uh, Carl Sauer's work, The End of the Ice Age and Its Witnesses, because it provides a very kind of an interesting perspective on this whole phenomena at that time, that sort of that bracket that's in the middle of the 20th century. So we're going to get right into that. This is Carl, by the way, and like I said, he was called the Dean of American Geographers, and I'm going to just read a few excerpts from this particular paper that he wrote that appeared in the Geographical Review, which is one of the well-established, long-established traditional journals representing geographical knowledge and geographical research. I found a lot of interesting stuff in there over the years. So, anyways, here is a few excerpts from Carl Sower's work, The End of the Ice Age and Its Witnesses. Currently, there is increased interest in the past that extends back into the Ice Age. Physical science has developed new and more exact means of inspecting the deposits of man and of nature, including tests to determine their age. Geophysicists and oceanographers especially have begun to examine and compare events on sea floor and land surface over a span of some tens of thousands of years. Using a principal measure, the loss of radioactivity in the contained carbon, radioactive carbon, or radiocarbon dating, he's referring to there. Thus, we are getting a revised and more orderly view as to the time and manner of the last warming of the continental ice caps and of their connection with the circulation of air and ocean waters in the northern hemisphere. Some facts of the presence and condition of the human witnesses of this interesting moment in geological time are now well located in the new chronology and invite attention to synchronous events in human history in the northern hemisphere. Synchronous events. What he's talking about is humans enmeshed in these great planetary shifts that are occurring synchronously. The transition from glacial to interglacial, dramatic changes in climate, in environment, in sea level, in the distribution of land and vegetation and fauna around the planet. What is the human counterpart of this? How are humans experiencing these profound planetary changes? That's what was interesting. Currently, there is increased interest in the past that extends back. Sorry. We are accustomed to distinguish Pleistocene time, or the Ice Age, from recent time by the disappearance of the great ice caps from intermediate latitudes. For the United States, the Ice Age is considered to have ended with the melting off of the last ice sheet within our borders, and this has got a geology term, which is the Mankato substage. And always when you see these names for these stages and substages and periods, periodicities in there, or a particular site that has been studied, you will usually see typically some geographical connection with the region, a town, a river, a lake, or some such thing. In this case, we're talking about study that would have been in the region of Mankato, Minnesota. So the Mankato substage. What happened in the Mankato substage? Well, it was during which our present Great Lakes were formed. You know what we're talking, the Great Lakes, Superior, Michigan, Huron, Erie, Ontario, the Great Lakes, and they are Great Lakes. Oh my gosh, they're Great Lakes. I spent a lot of time up on Lake Superior as a young person growing up and came to appreciate that that was truly a great lake in every sense of the word. It now appears possible to reconstruct in broad outline the physical geography of the United States at that time, dated as comprising the span from 12,000 to 10,000 years ago. Comparable data are available for the same period for Northern Europe. Although there is good reason to think that we are living today in an interglacial stage, we continue to speak of the present as part of post-glacial time. and of the last advance of the continental ice caps as the last glacial time. Little nuance here in our conceptualization of this. Post-glacial time doesn't imply, well, it implies that the glacial periods are ended. They're over. We're in post-glacial time. This is a new time now. Glaciers are a thing of the past, not a thing of the future necessarily. We continue to speak of the present part as post-glacial time, the last advance of the continental ice caps as the last glacial time. Well, the question is this truly a new epoch, distinct, separate, differentiated from the Pleistocene, such that we give it a whole new epochal nomenclature, the Holocene? Or is the Holocene part of the Pleistocene? In other words, if we look at the long-term evidence for glacial and interglacial transitions, what we find is that there were periods where the ice grew immensely, the temperature dropped enormously. This lasted for thousands of years or tens of thousands of years, and then it came to an end. The planet warmed, the ice caps melted, the sea levels rose, complete redistribution of flora and fauna and ecosystems, biological distribution around the planet, and now we're into an interglacial stage. So question is, how many interglacial stages have preceded the Holocene? And how frequently did they occur, and how long did they last? Might this be a question that would be of interest, say, to anybody who's involved in long-term thinking or long-term planning? I would say most likely the answer is yes. This is of enormous significance to ask this question. Let's go on with Carl's reading from Carl's paper. The physical geography of this end phase of the Ice Age may be sketched as follows. 1. The last ice advance over the interior of North America occurred much later than we have thought, as against a supposed age of 25,000 years or more, we must now accept one of about 11,000. Major change. The Ice Age was over by 25,000 years ago, right? 25,000 years ago, we were in the midst of a condition that we now know still existed at 11,000 years ago. With calibrated adjustments, more like 13,000 years ago. But you get the point.
Yes.
Right. It's much later than we thought. That's what it's dawning on these researchers. Oh, these events are a lot closer to our own time than we had previously assumed. As against a supposed age of some 25,000 years or more, we must now accept one of about 11,000 years. The Mankato ice advanced farthest south in a long tongue that pushed across south central Minnesota, which is Mankato is a town in south central Minnesota, and northern Iowa to the vicinity of Des Moines. Another tongue lapped about Green Bay and the north end of the lower peninsula of Michigan. A third extended across the Dakotas toward the Missouri River at Yankton. Now, these places that he's describing in the northern United States, what he's saying is that the glacial ice advanced and covered those areas. And then the ice sheet thickened as you went to the north and went thousands of miles, several thousand miles, all the way to the Arctic Circle. So if you're living in that region now, if you're living in Minnesota, you're living in Iowa, you're living in Illinois, you're living in the Dakotas or Montana, well, if you were suddenly transported back 13,000 years ago,
you'd be covered in ice.
You'd be covered in ice.
Yeah.
And that ice sheet it goes for several thousand miles, all the way up to the Arctic Ocean. Okay. The ice margin to the west and north of Yankton paralleled the course of the Missouri River. Look on a map, people. Follow the Missouri River. That almost outlines the most southerly extent of the Great Ice Sheet. And it's very interesting the Missouri River is an underfit river. It means that the modern river is flowing in a greatly oversized channel from that would be of commensurate size with the modern Missouri River. By means of the Altamont moraine, so we all know what moraine is now, meaning that certainly when you have moraine, that indicates the presence of ice, doesn't it? By means of the Altamont moraine and its continuation, this ice front has been traced into Canada beyond and to the east of Edmonton. This is an astonishingly deep as well as late penetration of interior North America, about 10 degrees lower in latitude than the maximum extent of the ice cap in Europe. So he's saying here in 1957, when he's looking at this and looking at how far south this gigantic mass of ice had extended, and then thinking about the huge volume and vast distribution of this huge, knowing it, remember, we're looking at from the Atlantic to the Pacific, a huge mass of ice with two ice caps. Remember, Laurentide, the big one, centered more or less over Hudson Bay. We've done the cool animation showing that it was at least a mile and a half thick.
Yes, and we'll actually integrate that right there. We'll show exactly what that is with that 30-second animation.
Excellent. So what Carl is saying here is that he was astonished at the depth of the ice right there where there is no glacial ice now, and how far south it penetrated into North America. Those two things were like, gosh. So it's looking at the vast extent, the geographic extent of this phenomena. At the same time, you're realizing that it happened quicker and later than you had previously imagined. So really the problem actually here is compounding itself on a couple of fronts. The realization of, my gosh, this mass of ice pushed so far south. But it did it and was doing that way more recently than we even thought a few years ago. So you can see how this problem is beginning to compound itself. And then that brought us up to 1960, and we were looking at the work there of Wallace Brecker, Maurice Ewing, and Bruce Heason. And this was where they had done the additional research into climatic change by looking at deep sea cores. And just as a reminder, before we wrap up this particular episode, let me read a section of it here. This scientific 1960 scientific paper presents evidence of a massive and sudden global climate shift that occurred approximately 11,000 years ago. By utilizing radiocarbon dating and geochemical analysis, the researchers demonstrate that the transition from the last glacial period was remarkably rapid. The study synthesizes data from deep sea sediment cores and changing water levels in Great Basin lakes, and pollen records from Europe, to show a unified warming trend. Now, let's look at these deep sea sediment cores going down just like we were talking about earlier. You go down, you take a core from the bottom of the ocean, you pull it up, and there are layers of sediment. And you can go in and you can analyze what is the constituents of those layers of sediment, and you can infer all kinds of information from that, right? The type of minerals that you see in there, the degree of refinement of the material. Are there coarse layers or really fine layers? Because one of the things that's being found in the North Atlantic is a succession of layers of much, much coarser material and then interspersed with thick layers of finer material, the kind of material that we see forming at the bottom of the oceans at the present rate of change. But interspersed with those, particularly in the North Atlantic, are these much coarser layers of material that appear to be granitic in origin. Now, how did those get there? Well, there's a good question, and we're going to explore that further. We have looked at some of the work of Willie Dansgaard. We're going to see these are called Dansgaard-Eschger events, and something is causing a major influx to coarse, gravelly material onto the ocean bottom. Then that's followed by a long period of what we would consider normal deposition, which is all of the living forms and inorganic forms that you might find in the ocean column dying and filtering to the bottom and forming these thick layers of very fine-grained sediment with microscopic diatoms and other forms of life and so on embedded within it. And then they're interrupted by these thick, gravelly layers. That tells us some conveys very important information about things that were happening in the environment outside the ocean. So we're coming back to that too and covering it. So where we're going to leave it for now is that from the quote from the paper, this is the paper titled in 1960. It appeared in the American Journal of Science, volume 258 in June of that year, in June of 1960. The abstract reads, evidence from a number of geographically isolated systems suggests that the warming of worldwide climate, which occurred at the close of the Wisconsin glacial times, was extremely abrupt. Surface ocean temperatures in the Atlantic Ocean increased by several degrees centigrade, and deep sea sedimentation rates sharply decreased in the equatorial Atlantic. The bottom waters of the Cariaco Trench, a restricted basin in the Caribbean, abruptly stagnated. The pluvial lakes in the Great Basin rapidly shrank from their maximum volume to nearly their present size. And you know, Mike, last summer we did that excursion exploring one of the greatest of the pluvial lakes in the western desert, which was Lake Bonneville. And we followed the route of the catastrophic Bonneville flood. Anyways, these are things that were coming into the forefront of scientific awareness during this time. Another factor that they had now noticed by this time was that silty clay, which was flushed into the Gulf of Mexico during the glacial period, was suddenly retained in the alluvial valley and delta of the Mississippi River, and the glacially dammed Great Lakes drainage was returned to the northern outlet as indicated by pollen profiles. A pronounced warm period in northwestern Europe also occurred at this time. In each case, the radiocarbon age determination suggests that the changes occurred in less than 1,000 years, close to 11,000 years ago. Keep those numbers in mind. Less than 1,000 years. From 10,000, 20,000 years, you can't see my hands, they're way out here, but compressed down to this, 1,000 years. Whoa, much quicker than we had imagined. And when? Close to 11,000 years ago. Calibrate that, and we're closer to 12,900 and 13,000 years ago. which puts us where, Mike? Right at the beginning of the Younger Dryas.
Boom.
Yeah.
So, Randall, I noticed in the past, or the papers you've been mentioning, I think from the early to mid 50s on up into the 60s, things like fairly abrupt change,
Mm-hmm.
which is over later years and more recent papers went to abrupt change. And then I've heard the terms extreme
Mm-hmm.
change.
That's what it's
And
coming
so
to.
we're heading somewhere
We are
with
getting
this, aren't we?
somewhere in this because we're seeing the unfolding of our understanding of these processes and how it's
Mm-hmm.
evolved over time. And to me, the interesting arc of this whole scientific inquiry into Earth history is that at the foundling stages of geology as a science, we
Mm-hmm.
find that the founders of that, the godfathers of geological science, were almost all, in some version or another, of catastrophists. And that's going to be a very interesting backstory. It's separate in a way from the focus of this series we're doing right now on the Younger Dryas, but it is extremely interesting and significant for a number of reasons. One, because they were looking at the world and the landscapes around them unfiltered by any kind of dogmas, any kind of accepted ideologies about, whether we're looking at a religious phenomena or a scientific phenomena, and where do we draw the line between theology and true scholarship, which was
So
always
the current climate change narrative hadn't really taken hold at that time.
Oh, no, no, not at all. Other than the
Yeah.
fact that coming out of the Little Ice Age, a lot of people were well aware of the fact that sometimes the climate could do extreme things.
Mm-hmm.
Extreme climate events and climate change is nothing new, believe me.
Right.
And in fact, recent years, recent decades, looked at within the larger historical context, also seem to indicate that we're in a relatively subdued period
Mm-hmm.
as contrasted with some of what went on during the Little Ice Age. But that's another area of discussion that we need to get into because to understand where we're at now, we're looking at the broad perspective of the framework of our thinking. Well, we can go to the larger scale and look at glacial interglacial transitions like we've been talking about here, but then there are smaller transitions within the glacial phases and the interglacial phases. For example, we talked of and introduced terminology from glacial to interglacial. And then when the changes that are occurring are not necessarily that extreme, we have introduced some new terminology, stayed or stadial and interstayed or interstadial, right? So here's the extremes. If this is interglacial, I'm going to go. If this is glacial on my left and this is interglacial, this is 15, 20,000 years ago, and this is now. We've got this degree of climate change from glacial to interglacial and back again. But we also have climate changes that are not that extreme,
Mm-hmm.
more like this instead of this.
Mm-hmm.
Those are the stades and the interstades. So a stade would be colder than an interstade, but it wouldn't be as cold as a full glacial.
Okay.
Uh, is that making sense?
Yeah,
Because
stayed.
climate
Well,
is not that simple between glacial and interglacial. There's all sorts of uh, nuances within those changes that we, if as scientists, you have to have a way of talking about things, and so you
sure.
need to have specific meanings associated. Well, we see that there are events where sea level has dropped from what it is now, but not 400 feet, maybe a couple of hundred feet. Well, that means that the ice has grown on the land, but it hasn't grown to the extent that it was during the full glacial, right? So there
Mm-hmm.
was ice. We know that because the sea level dropped. The eustatic level of sea level, the eustatic adjustment of sea level went down. Well, but there wasn't as much ice. There was maybe half as much ice, right? That would be an interstate, or no, that would be a stadial, sorry. An interstate is the opposite. Now, it could be a warming trend. Like, what if sea levels are 50 feet lower than now or 100 feet lower, but it's which would indicate a massive reduction in the total volume of ice, but not to the point where it disappears like the present condition, right? You still might have a small ice cap over Canada. You might still have residual ice up over northwestern Europe or whatever. Because if sea level is low, remember, more ice, sea level goes down. Less ice, sea level comes up. Those two are intimately connected with each other, right? So one gives us information about the other. If we see evidence that the ice sheets are growing, we know that simultaneously sea levels must be dropping. When we see ice sheets shrinking, evidence, and how do we know evidence of shrinking ice sheets? Well, we've been talking about this. We look at the simplest and most direct observation is the presence of moraine, because we can see moraine being produced today by living glaciers in the world today. We can see that when the glaciers were greater during the Little Ice Age, a couple of hundred years ago, the moraines were bigger and they covered a much larger geographic range. When we go back to the Great Ice Age, there's even more moraines. I was showing you some digital elevation maps the other day, remember? And we could see the remnants of the moraines from the
Right.
LiDAR analysis, which we're going to be looking at. Okay, but so we infer all of these changes from looking at these landscapes, and we can see changes in landscape mean changes in the atmosphere. Changes in the atmosphere and the landscape may imply changes in the oceans, etc. Because all these things are interconnected. They're all interlinked. You don't make a change in one area that isn't reflected by changes in other areas. So we talk about the terrasphere, that's the full sphere of all of the systems of the Earth, all the planetary systems. But then we might break that down and we say, well, the atmosphere, right? The atmosphere is the envelope of gases that surrounds the planet. We could say the biosphere, which is the living envelope of all the flora and the fauna that inhabit the surface of the Earth. We could say the hydrosphere, and it talks about the realm of water on the planet, which not only is the oceans and the lakes and the rivers, but it's also the subterranean waters, which we know are vast. But it's the entire linkage of the hydraulic components, the watery components of the Earth. We could talk about the cryosphere, which is the ice, right? We talk about the glaciers, we're talking about components of the cryosphere. So we look at the whole system and we can break it down into these manageable areas, but at the same time, we never lose sight of the fact that, yeah, there's an intimate connection between the hydrosphere and the cryosphere, right? There's an intimate connection between those and the atmosphere, between those and the biosphere.
So we really need to, as we seek to solve this mystery, you really have to have a holistic view.
Yes, you have to have a holistic view, and this is an encouraging trend of science. Is that you go back to mid 20th century and you know early 20th to late 20th century, and you see that science was progressively becoming more and more specialized. And each branch of science is developing its own nomenclature, its own language, its own vocabulary, which made it difficult for one scientist, to say a chemist or a physicist or an astronomer, to talk to a geology or a geographer. But now, what is happening? The encouraging trend is that there is more and more interdisciplinary cross pollination that is taking place.
It's needed.
It's
needed.
very much needed.
I mean, the medical establishment fell into the same mistake. You know, heart specialists, brain specialists.
Good point.
And they don't talk to each other.
And see, the way it's become is that, um, the hydrologist has a deep understanding of the role of water in multiple ways and places and in multiple contexts. The role of water, right? Well, the atmospheric physicist also, I mean, he's looking at a fluid, but his understanding is going to be considerably different. You're not looking at, for example, a hydrologist is going to look at the flow of water in channels, the flow of water in pipes, what happens when you change the gradient of a flow path, what happens when you change the diameter or shape, the hydraulic geometry of the flow path. You're not really looking at that, but in the atmospheric physics, you're looking at the jet stream, you're looking at atmospheric circulation and so on. Now, the thing that I would want to stress here is that, yes, we're talking about a holistic system, which means that all of these components intertwine and integrate in different ways. Now, if there's a common, shall we use the word pattern, to which all of these systems are somehow integrated, well, if you only know one component of it, you're not going to understand the larger pattern that links all of these things together. What links the marine realm to the atmospheric realm? Well, because you have gases that can pass the boundary of the ocean water, right? That's going to depend on pressure. It's going to depend on temperature. What is changing the temperature and the pressure? Well, the temperature can be changed by changes in carbon dioxide, for example, although not to the extent that is being proclaimed for purposes of propaganda, but it can be, temperature can be mostly affected. To me, the big driver of temperature change is the sun, because we know now that the sun, variability in the sun can cause changes in the temperature of the earth. Well, so you have variability of the sun causes changes in the earth's temperature. That now causes changes in the atmospheric chemistry. It causes changes in the temperature of the ocean, which changes the ocean chemistry, which changes the biological life within the ocean and how it's distributed. So all of these things are influencing and interacting with each other. So if you don't have a holistic way of integrating this, you might know a whole lot about one dimension of the whole picture, but you don't see the underlying pattern. And see, here's the thing, is you might be so intimidated by the fact, well, who can know all these different things? Well, here's what I think one of the insights
Randall Carlson.
Well, we here's what we can discern is that that if you can see enough of the broad spectrum of the picture, that you begin to get the outlines of the pattern. See, because if it's a pattern, if it's a consistent pattern underlying each of these different phenomena, that they're all connected by some of the same fundamental ratios, proportions, relationships, etc. Well, now we can begin to see the pattern that underlies the whole. And by means of that pattern, we can now gain insight into, without necessarily breaking down to that extensive detail, we can see we can gain insight into these other realms that we haven't necessarily immersed ourselves into the point where we can claim scholarship in that particular realm, if you understand what I'm saying. So
I do.
this work by Wallace S. Brecker, Maurice Ewing, and Bruce Heason came out in 1960. I'm going to move this over here. So this paper was evidence for an abrupt change in climate close to 11,000 years ago, and they brought a number of things that they had connected through. So,
is this your slideshow or is this not the slideshow?
not slideshow yet. I'm reading
Okay.
from it now. Then I'm going to pull up a slide in a minute here, which is going to be the pluvial lakes. So here were some of the things that they saw seemed to indicate that they were connected by a common pattern, right? Here was one. Surface temperatures in the Atlantic Ocean. They increased by several degrees centigrade at the same time that there was a major change in sedimentation rates on the bottom of the equatorial Atlantic. Then there's a restricted basin in the Caribbean called the Carriacou Trench, and it abruptly stagnated, which indicates that, okay, so if it's stagnated, it was part of before a whole system, a cycle of currents that kept that water oxygenated, that kept it flushed with new water, but now it's stagnated, right? Mm-hmm. Then they mentioned the pluvial lakes in the Great Basin, which rapidly shrank from their maximum volume to nearly their present size, which is today, because most of these desert areas do not have lakes in them anymore. Then something else they noticed, that the amount of clay and the type of clay that was being flushed into the Gulf of Mexico down the Mississippi River also changed at this time. And they saw that because the drainage of the area of the ice sheet in the area of the Great Lakes seemed to have suddenly changed direction from coming down the Mississippi River, flowing into the Gulf of Mexico and carrying all of this sediment down, depositing it, which incidentally the city of New Orleans is built upon this terminal glacial sediment that was dumped and deposited and built this massive delta in the Gulf of Mexico. That direction, the water flowing down the Mississippi River changed direction, and it routed through the Great Lakes and up through and out into the North Atlantic via the St. Lawrence Seaway. Why did that happen? Well, because that the glacier mass had shrunk back enough that it opened that outlet through the Great Lakes. And when it did that, the whole flush of water, which was many times greater than that now of the Mississippi River, suddenly diverted to the northeast and began to flow out into the North Atlantic instead of the Caribbean or the Gulf of Mexico. A pronounced warm period in northwestern Europe also correlated with this pattern of changes. And in each case, as they say here, the radiocarbon age determination suggests that the changes occurred in less than 1,000 years. Okay.
Mm-hmm.
Then this, in the introductory remarks to the paper, now we're going back to Brecker, Ewing, and Heesen. This is what they write. This paper summarizes the evidence for an abrupt worldwide change in climate close to 11,000 years ago, marking the end of the Wisconsin glacial period. That this climate change occurred suddenly was first recognized by Ewing as a result of the study of deep sea cores. From the evidence listed above, it is clear that a major fluctuation in climate occurred close to 11,000 years ago. The primary observation that both surface ocean temperatures and deep sea sedimentation rates were abruptly altered at this time is supplemented by evidence from more local systems. The level of the Great Basin lakes fell from the highest terraces to a position close to that observed at present. So we're going to look at that. Let's go to the slide now, and I will pull up a digital map of a three-dimensional map of the Great Basin, and let's get this. Let's define here what we're talking about. The Great Basin is this sort of a circular feature, other than the top here that looks like it's sort of pushed inwards. Of course, that could be due to the basaltic eruptions that created the Snake River Plain up here at the top of this image. But to get you oriented, here's Great Salt Lake right here. And all of these flat areas at one time or another held lakes. Now, the graphic I'm going to show you now isn't necessarily accurate, because I'm not saying that all of these lakes were at their maximum full pool at the same time. That was probably not the case because there was variability in the rainfall falling over this vast area of this interior basin. But we see basin and range. So basin is the flat area, the range is the mountainous area. This is all due to compressional tectonics that have squeezed almost like an accordion here and caused the uplifting and the upwarping of the ridges and the downwarping of the basins. This is also could be called a Horst and Graben geology, which are basically the same thing. You've got your upwarps and you've got your downwarps. Okay, so now this, and if we look at the Great Valley over here in California, which is now this major agricultural center and very fertile, it was filled with water. It was a lake. But what I'm going to do in the next graphic is I'm going to show you if all of the lakes were full pool at the same time, it would look almost something like this. Vast areas, really described more as an inland sea than lakes.
That's amazing.
With dozens and dozens of islands in it. When we did our Bonneville tour last summer, we focused on this area up in here, just this northeast area, which is where Lake Bonneville was. And we're not going to get into the discussion of Lake Bonneville specifically here because we're going to be preparing all of the footage and the stills and the drone footage and so on. Myself and John Arthur will be doing that, and we'll be editing together a presentation that will probably comprise 3 episodes of Squaring the Circle that were what we found traversing the field of Lake Bonneville. And then Lake Bonneville, of course, gave rise to the Great Bonneville Flood, which was a breach. Now, the interesting thing about this is all of this here, there's no outlet to the ocean. This is all inland, right? So if you have rainfall and this water pools up here in the Great Basin, it has no outlet to the ocean unless it gets really, really high level. But when it last did that, it did get high enough that it was able to find one low point in the rim. Out of the whole rim of this thing, there was one low point, and you can see it's right up here, right up in the northern rim of Lake Bonneville. And you can see this small blue line coming through, and that was a breach point of the Great Bonneville Flood that dispersed out over the Snake River Plain, carved the Snake River Canyon to the depth and magnitude that it is now. But this is all to be covered when we edit together the episodes on the Bonneville Flood, which is going to have a lot of in-field footage because we did this tour. We took, 40 people we took out, and we followed the route of the flood. We went through the Red Rock Pass here, emerged at the town of Pocatello, and then we followed the Snake River and followed the route of the Great Flood as it wrapped around the Snake River Plain and then eventually gets up to Hell's Canyon. And we didn't get that far on this trip. But anyways, this gives you an idea. If I go back here, you can see the Bonneville Salt Flats, which is the famous place for testing high-performance vehicles. Why? Because it's so perfectly flat. And the reason for that is because when Bonneville was at full pool, it was over 1,000 feet deep in places. Now, because of the fact that there was a lot of rainfall falling over the Great Basin at the time these lakes were forming, there was also accelerated erosion and material being washed off the range part of the feature. You're off the highlands and mountains. And this material is now going down and it's saturating the water that's forming these lakes. Well, then you have this major climate shift, and this is the climate shift that Brecker, Ewing, and Heesen are referring to, is that suddenly you had this massive expansion of the volume of water for a short period of time, and then it began to disappear, and it disappeared because the climate changed so dramatically from a fluvial environment with lots of rainfall, and that's clearly implied by the presence of these lakes to the desert dry areas that you see today. This is an extremely profound change, which, you know, yes, we can invoke explanations like shifts, latitudinal shifts in the jet stream, and that certainly played a role in it. But then that question becomes: are we back to the ultimate genesis of these changes, or is this just another symptom? The shifting of the jet stream is likely not a cause, but is a consequence of some greater driving force that's behind all of these changes that are now beginning to show up in all of these different areas geographically around the world and in dramatically different environments. So this is a final conclusion of Wallace Brecker, Maurice Ewing, and Heesen. They say this: correlation of all these systems on a finer scale is difficult. Certainly, if the abruptness of such a major change in world climate can be firmly established, it will be of the utmost importance that acceptable theories are able to account for it. Well said, but also understated. If the abruptness of such a major change in world climate can be firmly established, it will be of the utmost importance that acceptable theories are able to account for it. Well, one reason is because the kinds of changes that we're seeing here beginning to dawn on the perceptual range, the human perceptual range, is that the question that's implied is, well, what's happened before? Can it happen again? And I think we have to assume, I'll say what we shouldn't assume, what we can't assume is that no, what's happened before won't happen again. If we hypothesize or at least conjecture that it could happen again, then the next question would be, well, when could we expect it to happen again? Is this something that's thousands of years into the future, so we don't really need to worry about it this year? Is it millennia? Is it centuries? Perhaps maybe it's closer than we thought. Or is it decades? We don't know. We really don't know at this point. However, I agree with the authors here that it is of the utmost importance that we understand and we have theories that can account for what these changes are expressions of. What is driving these changes? So I think we've got a little infographic here to look at to help sort of grasp. There we go. The Great Climate Shift, evidence of an abrupt global change 11,000 years ago. And here it gets down to some of the specifics and the details in the Ewing, Brecker, Heesen paper. 6 degrees centigrade to 10 degrees centigrade rise in surface temperatures. Now, this would have been at the end of the Younger Dryas. Surface ocean temperatures in the Atlantic increased sharply at the close of the glacial period. Okay, so we haven't specifically tied the end of the glacial period to the end of the Younger Dryas back in 1960, which is what, 66 years ago now. There was a 50% reduction in sedimentation rates in the equatorial Atlantic, dropped by half exactly 11,000 years ago. Well, again, you need to add somewhere 2,000 years plus or minus a century or two, which of course then puts this right within the time frame of the Younger Dryas. And we can see here, North Atlantic right here shows evidence of 10 to 10, let's see what it's like. Yeah, okay, 110 centimeters in 10,000. Well, there's a little mistake there. It's supposed to be 720. So we've got studies from the North Atlantic, the Equatorial Atlantic, and the Gulf of Mexico, which show these changes in sedimentation rates. Well, those changes in sedimentation rates, the important point here is that those changes in sedimentation rates are implying changes in ocean circulation, changes in ocean currents. Okay. Then over here, we've got both terrestrial and biological evidence. The rapid shrinkage of pluvial lakes. This helps you to visualize the changes we're talking about here. When these lakes existed, there was also verdant shores with forests and trees and a whole environment there, right? Then you have the change from a apparently temperate climate to an arid environment. And as it says, near desiccation. So this could represent could be, Pyramid Lake, it could be Lake Lahontan, it could be Great Salt Lake, just mere dried up remnant puddles of what used to be there, right? So this change in landscapes, which here is depicted so dramatically, is implying a change in environmental conditions, including major changes in atmospheric circulation, amounts of rainfall, temperature changes, etc. And then we also see a reference here to the Mississippi drainage reversal. Glacial retreat cut off silt flow to the Gulf, returning drainage to northern outlets. And we'll be seeing more on that. We'll look at maps so you can see how the recession of the glacier, this would be the glacier as it receded, it allowed drainage to the northeast, where when these glaciers were at full extent, it blocked any other drainage other than that of the Mississippi River channel. And then you had this European pollen shift. So your vegetation profiles in northwestern Europe show a pronounced transition to the warm Alarode period. So before cold, coniferous trees and forests that are typical of northern climates shift to a much more temperate climate with more deciduous trees, warmer loving trees, and so on. So here's what's happening in 1960 to put all this together is that all of these different areas of study are showing the same thing, dramatic changes in the various systems. Now, in 1960, we're at the very beginning of realizing that there's this synchronicity in the timing and tempo of these changes, but we're in no position yet to be able to explain what ultimately is causing these changes. Are they just random, interconnected, and it's merely coincidental that they're happening and corresponding with each other at more or less the same time, or not? Because if it's not coincidence, then there's some unifying force that's behind all of these changes. And that's ultimately what we're very interested in this particular series that we're doing. And in fact, it animates everything we're doing, because what we're doing is trying to ask the vital questions that we as a human species need to ask and hopefully get answers to if we're going to have any hope at all of building a long-term sustainable civilization. And that, I think, is a goal that's worthy of our efforts. And if you don't believe that, I don't know what to tell you. You probably are going to find other places, distractions that you can find that you don't have to think about the big picture. But without the big picture and at least some percentage of humanity that looks at the big picture and has an understanding of the big picture, I would suggest or submit to you that our species would have become extinct thousands of years ago. So on that note, I will bid you all adieu for this episode of the Younger Dryas series in Squaring the Circle. We'll pick up where we left off, and we'll continue unpacking the research that brought the Younger Dryas from an obscure academic interest to right on the doorstep, right on the threshold of global change as we face it now in the 21st century. So until next time, we'll see you then. Be safe, have fun, and keep learning.